Hello guys, so I think I am now live, but I will check and let continue. Firstly, I'm checking let's I am live or not. Then wait 2 minutes and then we will starting our session. Hello, hello. Am I audible? Hello, hello. Am I audible? Yeah, so it's perfect. Now let's continue our session for today. So basically, the previous lecture I have taught you about the linear regression, like how linear regression works. So let's continue our discussion. Today is the date second. So here it is. I have teach you like what is the difference between AI versus ML versus DL. So now recap some of these algorithms, like what is linear regression. That's I have told you, and three types of machine learning also, like supervised and supervised reinforcement learning. So in supervised, basically our data is labeled; in unsupervised, the data is unlabeled. And the reinforcement learning is basically a penalty and basically we can say that a cost efficient algorithm. If you are doing a good back robot, then we give up basically a reward, and if I'm not doing a good back, then we have a penalty to this robot. And now this is the some algorithms I have taught you. So in supervised, these are the algorithms I have learned. Linear regression, today I am going to explain you like regional lasso, elastic net, and logistic regression. Think I have covered. And so this is the algorithms. So now the question arises, like this is impacted by outlier. So yes, because if I suppose outlier bit, I will take my pen and then we'll continue. Where is my pen? Yeah, this is the pen is there. Okay. So I will take my pen. Hmm. I have to take a line only, not darker. Yeah, this is perfect. Suppose a outlier, suppose here it comes. So by coming to this outlier point, your line will be shifted like this. So because of only one outlier, suppose your line will be looking like this. So this is impacted by outlier. So that's why we have not used this linear regression if your data has some outliers. And to reduce this outlier, like they to reduce this outlier, like we we have used some legend lasso regression to overcome this. So now today we will learn about this. We can say due to the impacted of outliers, and this is the cost function that we have used, that I have already told you, and this is the gradient descent function. Learning rate I have already told you all of these things. See my previous lecture if you want to learn of these things. Where we are now multiple linear regression also told you, like now performance matrix, that I have told you. Yes, performance matrix also, like r square and adjusted r square. Based on this we have to calculate the performance of our model. So like in your mind the question will arise, which is good R square or adjusted R square? Adjusted R square is the best metrics that we have used to performance measure the performance of our model. And this is the formula. Because if the number of variable is increasing, then the basically your model will be calculate the accuracy by good performance. And now overfitting and underfitting also we have learned. This is done. Now polynomial regression I think also done. Like if the we have all also, yeah, I've done it. Basically in polynomial regression the number of variables like independent variable only increases and the rest of the algorithm is same as the regression. Now I think here we are. So now today we will continue MSE, MAE and RMSE. What is MSE? Mean squared error and mean absolute error or root mean squared error. So what is this? So in mean squared error basically we square the error, and in mean absolute error we basically take a mod of this error, and RMSE basically we take a firstly mean square and then take a root of this error. Basically this is. So now like how to calculate this, all of these. This is the cost function basically we use. So basically MSE mean squared error used to find the gradient. Like we can say that a gradient function, you have a quad gradient, we can say what we say, this function gradient equation, or we can say but we can say, I don't remember the exact name, but I think gradient descent, yeah, gradient descent we say, quadratic equation which is differentiable. And to use this MSE, so basically MSE is used in to find the global minima of this equation. Also we can say advantages, because it is basically MSE is differentiable, because basically this is a squared function, so you can differentiate, and it is a one local and one global minima. If you plot this function, then this will look like a quadratic. Basically this is a quadratic equation, so which will looks like a convex function. Disadvantage, not robust to outlier. Yeah, we are already told that if your regression line will come, like if your data point will come outlier, then the your line will be shifted to this outlier. So that's why this is not robust to outlier. It is not in same unit. Yeah. So basically, if your independent variable is in a different unit, then this will not work well. So to reduce this like not same unit, we will apply some like transformers, not transformer, we can like normalization, standardization to convert this all of this value into a same number format. So that's for it. And for like why we don't apply like this function, we can say a gradient descent function in logistic regressions, because of this the non we can say that logistic regression will have a non-convex function. Basically the formula to find a error is basically in, we cannot apply this function basically MSE or RMSE in logistic regression. We apply this some another function to find the error in logistic regression. That's why it's for logistic regression only. And mean absolute error, I have already told you. Robust to outlier, yes. Mean absolute error, RMSE. And these are some advantages. Same unit, differentiable. Now continue our discussion in ridge regression, lasso regression and elastic regression. So today now continue our discussion on ridge regression, lasso regression and elastic net regression. So now continue, like this is our gradient function, gradient descent function we already know, and this is our global minima, and linear regression looks like this. So basically, ridge and regression basically comes in picture when the data have a overfitting condition. So suppose you have a data and you have created a linear regression line and the data have a overfitted, like your model will be overfitted. Overfitting condition means your training accuracy is high but testing accuracy is low, like, or we can say a low bias high variance condition. Low bias means basically training data have a good accuracy. Basically, the suppose your training data set comes a 95% accuracy, and when you tested this model you will get approximately 80% of accuracy. So this condition basically known as overfitting. So to reduce the overfitting, we have a two, or we can say a three types of models, or we can say techniques to reduce this overfitting. The first one is ridge regression, the second one is lasso, and the third one is elastic. We can say basically the two techniques, ridge and lasso. Basically, everyone use. Elastic net is also used, but is not in a good, like, a very low percentage. We can say that are uses of elastic net. So now coming to ridge regression, like how? What is ridge regression? So basically, ridge regression, also known as L2 regularization, or can to basically we apply this techniques to reduce the overfitting. And we have already told you this one. And so suppose this is your best fit line. So according to this, your model is performing well on the testing, and at the time of testing the model is not performing well. So by ridge regression, when in your mind ridge regression will came directly, L2 regularization also came. Like ridge regression is also known as L2 regularization. L2 regularization in your mind will came, so directly L2 means is L2, 2 means square. So the cost function will look like this square of this cost function. That's it. So suppose you are training a model and your m value is getting 0. So at the time m value, like, you will get some equation and you will get m equal to 0. So m equal to 0 means you have error 0. Suppose, so to reduce this overfitting condition we apply some condition like this. In the cost function we have added something like hyperparameter lambda into slope of summation of slope of square. Summation basically we taking, if we suppose we are taking, supposing we are applying a multi-class classification algorithm, that's why we have taken the summation of slope square. If you are using a only a simple linear regression, then you can take only a slope square, lambda into slope square. So basically this is the hyperparameter lambda. So hyperparameter means you can change at the time of training. So this is hyperparameter, and according to this, suppose this is the function of lambda equal to 0, lambda equal to 10, lambda equal to 30, you will get this like function. And so that's why suppose this is the equation and theta 0, theta 1 and something like that. So like at the time of cost function we will apply this function also. So lambda is fixed every time and you will get something like this equation. So basically we have added slope square. So overfitting, if you suppose model is overfitted but we have added the slope square, so by adding the slope you will not your model will not be fixed, your line will be shifted toward the slope. So that's why your model will never get overfitted by applying a rigid regression. And the second one is lasso. So also lasso regression, also known as L1 regularization. L1 regularization means basically we have to apply lambda into mode of slope basically. So here the summation of mode of slope. So this the equation like theta 0, theta 1x, theta 2x, and also we can apply uh, this ligation and lasso. Lasso means L2, L1, L1 localization. So this is also used for feature selection also. The first aim is to apply a lasso regression is to calculate to reduce the overfitting, and the second profit is to apply a lasso regression is feature selection. So like how feature selection work and how overfitting will be reduced now comes. So lambda already we know this is a hyperparameter you can change at the time of training, and this is the lambda of like mode of slope. So like how mode of slope work. Mm, so mode of slope we are there, okay. So how mode of slope work basically the question is that, and how feature selection is done by lasso regression, this is the question. So suppose in the ridge regression we are squaring our slope, but in lasso we are not squaring. So if your theta 2 will be approx to 0, suppose 0.002, so it will be approx to 0. So it is automatically be deleted at the time of applying this function. Basically it's a negligible, we can say it's a negligible change. So you can, if you this is a negligible change you can delete it. So that's why feature selection is done. If your feature has a q, basically slope has a high, then it's automatically be taken, but it's a low value, then it's or automatically deleted. So that's how feature selection is work. And by applying this formula, it's slope of like mode of slope, the basically regularization of that your model line will be shifted toward your errors. So that's the your model will never be overfitted. That's how it's work. And now the third type is elastic net. Basically, elastic net is also used for reduce overfitting and feature selection. How? Basically, this is a combination of both ridge and lasso regression. That's it. And hyperparameter tuning, the linear regression. So lambda is basically lambda 1 and lambda 2 we have changes. This is hyperparameter. Now coming to type of cross validation. So cross validation basically means we have changed. Basically, cross validation at the time of training, you have a function in scikit-learn. Inside the library scikit-learn, there is a cross validation and something cross validation is there. So by applying a cross validation, you can change different types of values like uh, lambda. Firstly, you can change 1, 2, 3. Every lambda you can uh, fit it, and by applying a cross validation, the model will be gives a good parameter, taken a good parameter according to your given cross validation parameters. That's how. And data set basically 70% is used for training and 30% is used for testing. Or also you can divide this training data set into train and validation split. For this you can change it according to you. Just basically all of this depends on you. This is basically also a hyperparameter. Leave one out, cross validation. P out, CP cross validation are there. So leave one out cross validation is also there, or also we can say that's a k cross validation. So in this data set, basically if your data have 100 points, so firstly we will give 90% of data set and 10% of data set to testing, and or we can say that's a for validation. And for the second time we take this another data set to validation, and other data set like it is 90% like this first 10 data set. Suppose their data set you have like 0 to 10 points and 10 to 20 and 20 to 100. So every time you give 10 data point to validation, in the next epoch you will give this data point to your validation, and in the third epoch you give 10, 20 to 30 data points to your validation data set basically. Now coming to overfitting, training accuracy, and this is the new data set. Yeah, that's it. K-fold cross validation, that's I have told you now. And experiment is the same. K-fold cross validation, time series cross validation, performance metrics, accuracy, precision, recall, and F beta score. Now we will learn topic to be covered today. This. So now learn performance metrics. Inside the performance metrics, we have accuracy, precision, recall. So basically, this all of these topics comes inside the logistic regression. So logistic regression basically used for binary class classification. Also, you can use for multi-class classification, but most of the time we use for binary class classification. Basically, the logistic regression model. And suppose this is your data set, x1 x2 are independent feature, and y is basically a dependent means your output feature, and your model will be predicted like one you this is your actual, and this is was the predicted feature. So according to this you have created a confusion matrix basically. Here is the true positive, true negative, false negative there, and basically this is the actual value 10, and this is the predicted value. And also r squared registered r square also learn. So that's for logistic regression. And now I have already told this is a true positive column. Basically, this is your actual and this is your predicted. So true positive, like your actual value is 1 and your model is also predicted 1. So we can say true positive, true negative. This basically in a diagonal you can see that these are values basically correct one, and these are the incorrect predicted by your model basically. And this is the formula to find the accuracy. True positive, basically why this color font is coming big. So this is the formula to find the accuracy. True positive, true negative, false positive, false positive, false negative, and true positive, like divided by all of these values. So accuracy we already know, like the total number of correctly classified upon total number of points basically, we can say that's accuracy. And so accuracy is basically very easy to find. And binary classification, thousand data. And so now the basically question will arises, like suppose if your data has imbalanced data set, like suppose 900 classes have 1 and 100 classes have 0, and if you find now the accuracy, if you even your model will not be accurate, you will get a 90% of accuracy. That's the problem if you get an imbalanced data set. So to reduce this imbalance data set, we have some other techniques to find the accuracy, like precision and recall is there. So what we have done in precision, basically precision is basically true positive by true positive plus false positive. So out of all the actual, how many are correctly predicted. So now I will explain you like what is this formula precision. To find the precision, basically we have true positive values upon true positive by false positive. To remember this formula, you can learn a story like this. Precision, true positive by true positive. True positive everywhere is coming. If you apply find a precision or recall, so true positive is there every time. So true positive divided by true positive plus false. Up now here will be changes. False positive is coming or false negative. So precision P is coming. In precision P will be came. So to remember this formula, you can create a story like that. And for recall, what will come? Opposite one, like P is there, then false negative will come. That's it. To remember this formula, you can create a story like that. So that's done. And like in recall, the formula is false negative. I've already told. So now, what the use cases of this precision and recall? The question will arises now. Where we have to use precision and where we have to use recall. This is the biggest problem, and many interview will confuse you this problem. They will ask, they will know you will be confused in this problem, so they definitely they will ask you, like the name suggests is confusion matrix, that's why you will be confused every times. So now I am explaining you, please listen carefully, every my every word listen carefully. If you get confused, then maybe everyone will be confused, so listen properly what I am telling. So basically now listen, if you, there are many types of problems. Suppose what the use of precision, the first. So where we have to use precision and where we have to use recall, the question will be this: in which problem we have to find precision and which problem you have to find recall. The question is only that's it. So I have told you the formula. Formula is basically true positive by true positive plus false something will came. So in precision p will came, so false positive will came. So you have write a formula like this: true positive by true positive plus false positive. Now what will came, like you have suppose a two problem, like first one is mail spam or not, and the second one is cancer detection. So now which will have to calculate, like suppose you are solving a problem mail, then which is important, precision or recall? To find precision is importance or recall, we have to give a recall importance in a spam mail hem spam hem classification problem. Listen carefully now. I have focused on this word only. If you finding a precision, then focus only on this word. False positive. False positive. If the false positive is importance, then calculate precision. If the false negative is important, then calculate the recall is important. But that's it. Now how do I know like false positive is important or false negative is important? Now this question, like everywhere is story. Firstly the question will arises like which is important, precision or recall? If you, so in precision, if the false positive is important, then precision is important. If false negative is important, then recall is important. Now how do we know the false positive is important? To find this false positive, you have to think this one. False positive, suppose you are doing a spam ham classification. So this is your actual classes and this is the predicted one. This is the predicted and this is the actual. Suppose you get a mail in your inbox which is not a spam, not a spam. Like you get a job offer from any company and you have created a model which will predict something like spam. You get a job offer from any company and your model will be predicted as a spam, and you can't able to see this message because this is in your spam folder. So this is the biggest problem that your model will be predicting. So in that case spam ham classification false positive is important. So the spam ham classification will, when you are doing a spam ham classification, you have to calculate the precision. That's it. Now suppose you are doing another problem like cancer detection. So now again the question will arises, what I have to calculate? The precision is important in this problem or recall is important? So again you have to create a story like that. Now false positive importance or false negatives. Now again, firstly calculate this one, false positive for the cancer. Suppose this is a cancer and this is not cancer. This is, your model is predicted cancer and not cancer. So you have not cancer, you haven't a cancer, but your model said that you have a cancer. So what will happen? You will go to doctor again and check up again. So you are able to know that okay, I have not a cancer. Still your model is predicting wrong, but that's not harm. Like your model is predicted you have like not not cancer, you haven't a cancer like actual class, and your model is predicted cancer, you have a cancer. Like suppose that somebody said you have a cancer, then you will go to again for checkup. That's it, the process that we have to follow. But suppose you, you have a cancer, here the actual class, you have a cancer, your model predicted you have not a cancer, false negative. So in that case, what will happen? You have cancer, but your model is predicted you don't have a cancer. That's the problem. Like now, what happened? You will you have a cancer, and the model will predict you don't have a cancer. So you don't go to doctor, or even you will be free. But after 2 3 years, this will be a big headache, because now the cancer will be go to a third stage, and you can't do it anything. So this is the biggest problem. So false negative is important when you are doing a cancer detection. So that's why you have to calculate the recall in the cancer detection. That's the story that I have created, and I think you will able to understand my story. If you are not getting, then see it from where I have starting, like where I've said, please listen carefully. Basically I have understand this story in a very good manner. If you are not able to understand, go to again and learn it. I think I have explained in a good way. So that's the story. Mhm. Mhm. Okay guys, now continue our discussion. Truth, diabetes already I've said. Now coming to f of beta score. So f beta score formula is 1 plus beta score precision into recall upon precision plus recall. So if you apply a beta equal to 1, then you will get a HM, basically harmonic mean of this precision and recall. Twice of precision into recall upon precision plus recall. So basically this here you have giving equal weightage to precision and equal weightage to recall. And suppose if you want to give higher weightage to some time precision, like suppose here I have given importance, we have learned like precision and recall. But suppose you want to give like we can say importance to both precision and recall. If you want to give equal weightage, then you apply beta equal to 1. And if you want to give higher weightage to something like precision or recall, then you apply some beta is there. If you apply beta is greater than equal to 1, then here if false negative, you are giving false negative is a high precedence. And if your beta value is lower than 1, then you are giving high precedence to false positive. Now the question is like how, but I will tell you. Basically everything, machine learning, AI, ML, data science, anything. If you are learning, that's good. Anything like math, physics, chemistry, anything you are learning, every time the question will be how. If you are stuck, like if you learn something, like I have said, if the false negative is greater than false positive, if you want to give high precedence to false negative, then apply a beta greater than 1. And opposite to this, like if you want to give high precedence to false positive, then give high precedence, like apply a beta less than 0. So the next question every time in your mind will come like, why, what the, like why I have to apply this beta greater than 1, or in this case beta is greater than 1 or greater than, like less than 1. So see this formula, precision and recall. So in precision, basically false positive will come. We know false positive will come, and false positive will came in denominator basically. So the denominator may false positive is came. So suppose you apply beta equal to 0.5, and beta is here like 1 plus beta square precision. To recall the formula is incorrect, basically it is beta also there here. Beta square is also there here, beta square into precision plus recall, this is the correct formula. So beta square is there basically. So if you apply beta equal to, suppose greater than 2, greater than 1, 2, 2 into 2, 4 into precision, and the precision, precision is basically true positive by true positive into false positive. So it is opposite to false positive basically. Hmm. So beta square into opposite, like upon, so if you apply something like that, you will get a big number. So here false negative, if you get apply like 2 into 4, it is opposite to like false positive. Opposite to false positive means opposite to false positive. So you have to do opposite, like you are giving high importance to precision, but this is in coming in denominator, so it is opposite, like so you have to give high precedence to false negative. That's the for, that's it. Now logistic regression for multiple multivariable, like one versus rest, or you can say that. So if you are doing a linear regression for multi-class classification, then what you have to do, just change something. So in that we apply a one versus rest. So firstly we have calculate, draw a line, something like that. Here we have created our line, and for this line, this will comes to a, in one category, and this all points come into the second category. And the next time we will apply something like that. So this will come into the another category, and this all point will be come to the second category. And the third time you apply, so this is one versus rest. At the time you take in one and take another into a rest of this column. Same as if you are doing also 4 5 classes, then you can also do it in the same manner. One versus rest, logistic regression, M1 M2 M3 is there. Output O1 O2 O3 O1 O3 O2. New test data, M1 M2 M3. Logistic regression already I have told you. Now how logistic regression solve classification problem. So this is the formula. Like, firstly, we have created a line. I don't know why this is coming here. Firstly, we have to learn this, and then we have to learn confusion matrix. No, no problem. We can continue. Not a problem. To use. Channels live. Channels live. One watching now. Hello, bro. Can you comment it down so I am able to know who is watching me now? Shh. Okay, so let's start our discussion. So, in logistic regression, we apply a linear regression line. Same as suppose this is the study of hours you are getting, and if you study less than 4 hours, you will fail, and if you study uh, like more than 4 hours, you will be passed, something like that. But suppose if you have get a outlier, something like that. Due to this outlier, your line will be shifted like this. So now, if you now your model will be saying that if you will study even 5 hours, you will get fail. This is the problem in logistic regression. So it is sensitive to outlier. Basically, if your model has outlier, then don't apply linear regression line basically. So to reduce this, they have applied a sigmoid function. So basically, what does sigmoid function do? It will be squeezed like this. So if you now will get outlier, your model will not be impacted by outlier now. Still, if you apply this formula, it is still showing like this. So now by applying a sigmoid function, you will not get something like that, which will able to solve a problem basically. Hello, bro. I will call you later. बाद में कॉल करता हूँ मैं. Okay, bro. So we are near. Like this is not impacted by outlier if you apply a sigmoid curve. So this is the sigmoid function 1 upon 1 plus e raised to the power of minus z. Linear regression cost function. So we have seen that in linear regression we apply this error function basically h of theta x basically a predicted value of minus actual value ka whole square. And logistic regression cost function is same also, but we did not apply this one. Why? The for again the question will come like why we don't have to apply this. So basically, if you apply this error function in your logistic regression, then the curve will something like look like this because there is a exponential function is there. So if you do a derivation of this function, you will get us something like this. Many locals minima you will get, or you can say that non-convex function. Basically, this is a convex function and this is a non-convex function. So interview will ask why you don't apply a gradient descent or basically a gradient descent function in logistic regression. So you can say that this cost function will looks like a non-convex function, or basically there's a many more local minima. So we will not get a global minima. We will stuck in a local minima. That's why we don't apply this logic cost function in logistic regression. So in logistic regression, we apply another cost function. The formula will be minus p log p minus 1 minus p log minus 1 minus p, which will be looks like this. P, or we can say that minus by log minus predicted value minus 1 minus by log minus 1 minus by. Basically, this is the formula. So we apply, this is the now your cost function minus 1 upon 2m summation same this one, and you derivate this function and you will get now cost function which will looks like same as your above one. So this is and repeat until convergence, and convergence means you will until not get a global minima, you have to repeat this process basically. So that is the logistic regression, and also I have told you this what we can say confusion matrix like accuracy, precision, recall, F beta score. This already I have told you. This is to find the accuracy of your logistic regression model we have used. Okay, so that's it for this lecture. Now we'll continue third lecture after some time. Thank you guys. Bye bye. Love you guys. Please motivate me by subscribing my channel. If you will subscribe my channel, I will be motivated and will create a content like this. Like if you watch this video, then you will get a in-depth intuition about confusion matrix. Here I have explained a confusion matrix in a very good manner. If you will see my lecture, you will not never be stuck in confusion matrix basically. थैंक यू गाइस, मिलते हैं नेक्स्ट लेक्चर में.